Let's look at how we can use some of the properties of exponents and logarithms to solve exponential and logarithmic equations. Here are some major properties we will rely on as we solve equations. The first is the one-to-one property for both exponential and logarithmic functions. Because these functions are one-to-one, that means output values of these functions, here represented by b to the s and b to the power of t, are equal if and only if input values are equal, if s equals t. This is also true for logarithmic functions as presented in an earlier video. We may also recall the inverse properties that log b of b to the x is equal to x and b to the power of log b of x is equal to x. Let's look at a few examples of exponential equations and apply some of these properties to our solutions. Notice here that the bases are the same in this equation, and so because of the one-to-one property, I can set the exponent pieces to be the same. The bases are the same, the two sides are equal, therefore the exponent pieces are the same. So we have 2x minus 3 equals 6 plus 5x, and I can simply solve this as any other linear equation for x. We'll rearrange some terms here, and we get negative 3x equals 9, which leads us to a solution, x equals negative 3. Let's see if I can apply the same idea with another exponential equation. 8 to the power of x plus 2 equals 16 to the power of x plus 1. If I can express these bases as powers of the same base, then I can use the one-to-one property of exponents to solve for x. So think about the numbers 8 and 16. Both of these are powers of a smaller base. 8 is the same as 2 to the third, and 16 is the same as 2 to the fourth. So on one hand, I have 2 to the third to the power of x plus 2 equals 2 to the fourth to the power of x plus 1. And we can multiply those exponential pieces together. So I have 2 to the 3x plus 6, distributing the 3, is equal to 2 to the 4x plus 4. The one-to-one property of exponents comes in here. Since the bases are the same and the two sides are equal, the exponent pieces must be the same. So we can solve the equation 3x plus 6 equals 4x plus 4. Rearrange some terms. We get negative x equals negative 2, therefore x equals 2. In our final equation, we have only one exponential piece, so we need a different approach here. I want to try to solve for x by isolating the x value and having everything else on the other side of the equation. First, we can subtract 8 from both sides. I have e to the power of 1 minus 2x equals 12. And because these two sides are equal, I can apply a logarithm to both sides of any base that I like, and the logarithms will be equal. Why don't we apply the natural logarithm? So the natural log of e to the power of 1 minus 2x equals the natural log of 12. Now, the reason I chose the natural logarithm is because that's the inverse of the exponential function with base e. One of the properties that we solve for logarithms is that the natural log of e to the power of something equals that something. So the natural log of e to the 1 minus 2x is the same as 1 minus 2x. And that allowed me to begin to isolate the x value and solve for x here. Let's subtract 1 from both sides. I have negative 2x equals natural log of 12 minus 1. These are different terms here. Natural log of 12 represents some number, and then I'm subtracting 1 from that number Let's solve for x by dividing by -2. I might write my solution in this way. I'm going to say it's the negative natural log of 12 plus 1 over 2. Or you could say it is 1 minus natural log of 12 over 2. This is considered an exact solution for x. I could get a decimal approximation of this by plugging these values into a calculator. But if I'm asked for an exact solution, here is how I will represent it, understanding that natural log of 12 is a number just like any other rational or irrational number.